we were calculating a one particle partition function for an ideal gas, and we had come up with an expression like this, and I had said that we can take each of these terms individually and evaluate the integral and take the product of the three integrals. When we do that, the evaluation of, let's just say, this first term here for Lx will give me V over, I should say Lx over 2 pi h bar, 2 pi m over beta. And that's to tabulate that integral. If I do it for all three integrals, so over Lx, over Ly, Lz, or Kx, Ky, Kz, as the case may be, I put that all together, and this turns out to be my one particle partition function. If I want to calculate the mean energy, what we need to do then, first of all, we'll calculate log z. Log z turns out to be n times the log of v over n minus 3/2 log beta plus 3/2 times the log of 2 pi m over h bar squared plus 1. Now, to find thermodynamic quantities, I have to take partials with respect to log z. So if I take the, to find the mean energy, that's going to be minus the partial of log z with respect to beta. That will give me 3n over 2 beta, which of course beta is kt, so it's going to give me 3/2 nkt, which we would expect for a three-dimensional gas. Entropy, we know the expression is k log z plus beta e. That will turn out my mean entropy. Let me write that over here. My mean entropy, if I were to write that out, would be equal to k times log z plus beta e, which I can write as n times k log v over n plus 3/2 log t plus sigma naught, where sigma naught is constant equal to 3/2 log 2 pi m Boltzmann's constant h squared plus 5/2. Okay, these are the answers that we got when we incorporated the n factorial to alleviate the Gibbs paradox back when we did classical statistics. So it's turning out exactly the way we would expect it to, except we use quantum mechanics to get there, which is going to be more correct. So let's talk about the physical implications of the quantum mechanical density of states. First of all, you don't get the Gibbs paradox in this case. S behaves like an extensive parameter, right? We've got this v over n, this ratio of those two, so the log of that is not a problem. If I double v and I double n, I still have an extensive parameter. For entropy, it turns out that I have no arbitrary constants in the partition function or in S. Z is a well-defined quantity, and it contains Planck's constant. You remember when we did the classical statistics earlier, we used a h naught cubed for our as part of our element for coordinates and momenta. This now we know what that is. That's Planck's constant. We didn't know that earlier on. There was no Planck's constant in classical physics, of course. And this is going to be important in dealing with phase changes, because we can write our chemical potential is now minus kT log of E log Z dN at constant volume temperature. And therefore, I can write this as minus kT times log of zeta over n. So these are really nice quantities that we get from using quantum statistics even at the classical limit.